for now. Let's just focus on equivalence principles. What is an equivalence principle, and what role is it meant to play in the foundations of space-time theories? Well, good question, and people have been asking these questions and debating about them for a very long time. But what should be uncontroversial is that alongside other principles, such as Mach's principle and the action-reaction principle, the equivalence principle was a critical heuristic device in Einstein's path towards general relativity. All parties agree on that. It's only after that that people start to disagree. Some people think that in the completed version of, say, general relativity, the equivalence principle has absolutely no role to play, whereas others have quite contrary opinions. So in the first camp, no talk on the equivalence principle would be complete without this quote from Synge. So Synge wrote, "The principle of equivalence performed the essential office of midwife at the birth of general relativity, but I suggest that the midwife be now buried with appropriate honors." So Synge believes that in the completed version of general relativity, the equivalence principle doesn't have much role to play. Insofar as that's meant to apply to all versions of the equivalence principle, I disagree with the claim. It seems to me that the equivalence principle has an important role to play both in articulating or understanding the content of one particular space-time theory, but also in understanding the connections between different space-time theories. And so it's with that more positive attitude in mind that I kind of want to proceed in this talk. The goal is going to be the following. I want to present a framework for understanding equivalence principles, which, first of all, is equally applicable to both the relativistic and the Newtonian contexts. So there's been a huge amount of work on relativistic equivalence principles, but the literature on Newtonian equivalence principles is still quite nascent. Most of the recent work on this has been done by Eleanor Knox and Simon Saunders, and Fox and Stachel as well. Yes, so I want to present a framework for understanding equivalence principles, which is just as applicable to the relativistic context as to the Newtonian context. I would like this to subsume a very, very nice recent paper by Dennis Lehmkuhl, in which he presents a classification of equivalence principles. It seems to me that Dennis is bang on the money in that paper, so I would like to incorporate as much of it as possible. I would also like to subsume Eleanor Knox's very nice recent work on equivalence principles. So Knox, to my knowledge, is the first person to talk about strong equivalence principles in the Newtonian context. And I want to take on board the lessons which she draws in her 2014 BJPS paper. And finally, I'm not going to say too much about this, but I think that there are some interesting connections with recent work by Weatherall and by Wallace. So what's going to be the glue which ties all of this together? It's going to be some work which I did with Nick Tay for understanding in more rigor what it is to geometrize and de-geometrize a space-time theory. In fact, once you've got that stuff on the table, the rest of what I say is maybe kind of trivial. I think that it will pretty much be known to people like Eleanor already, but we can definitely be more rigorous about things by using this work that I did with Nick. So here's the plan. I'm going to start off by reminding you about general relativity and Newton-Cartan theory. A lot of us will be familiar with this stuff already, so I won't take too much time over that. I will then talk about how we can subsume a theorem in the Newtonian context, which is known as the Troutman recovery theorem. This is the work that Nick and I did. And then I'll present very, very briefly some applications of that. So that takes us to the end of the third section of the talk and about the first half of the talk. After doing that, I will then turn in earnest to the project of looking at equivalence principles. So in the fourth part of the talk, I'll talk about Lehmkuhl's framework for equivalence principles, and I'll add a few more into the mix. I'll then show how to apply this both to the Newtonian and to the relativistic context by using the stuff that I developed in the first half of the talk. In this section, refined equivalence principles, and then I'll close. Okay, so general relativity and Newton-Cartan theory. Here's a framework which we're all very, very familiar with, the distinction between kinematically and dynamically possible models. So kinematically possible models of a space-time theory picked out by tuples of a manifold and then some geometrical objects. So a manifold phi and then various fields on M phi, sorry, a manifold M and various fields on M phi 1 to phi n. And then the dynamically possible models of a theory given by those kinematically possible models in which the phi's satisfy certain specified dynamical equations. Okay, so in the differential geometric formalism, here is, with that distinction in mind, how you would present Newtonian gravitation theory. It has kinematically possible models which feature 6 objects. So I have the manifold M, a one form T, which represents Newtonian absolute time, a spatial metric field H, degenerate, which represents distances between points of absolute space. I've got a derivative operator nabla, this field phi, which represents the gravitational potential, and this field rho, which represents the matter density content. And these fields satisfy an orthogonality relation and then these compatibility relations. Then dynamically possible models of this theory are picked out by this guy, which is the Poisson equation, a condition that the derivative operator be flat, and this third equation, which says that gravitating but otherwise force-free bodies do not move on geodesics of this connection, but rather they deviate from geodesics in accordance with this term associated with the gravitational potential. Okay. So those of us who have studied the foundations of Newtonian mechanics will be familiar with Leibnizian static and kinematic shifts, certain symmetries of Newtonian mechanics set in Newtonian spacetime. The next level up symmetry is what Huggett calls a dynamical shift, and is what other people call Trautmann-gauge symmetry. And it takes this form. If I scale my gravitational potential by this term psi, and I change my derivative operator, then I get something which takes solutions to solutions. Effectively, what I'm doing here is I'm kind of uniform, or I'm linearly accelerating everything and then changing my standard of straightness. So this symmetry is known as Trautmann-gauge symmetry. If I did these two moves, I would get something which was empirically equivalent to the original model. So this is a gauge freedom in Newtonian gravitation theory. In order to eliminate the gauge freedom, the standard story, just as with the static and kinematic shifts, is that I need to reconceptualize the space-time setting of Newtonian mechanics. And what people normally go for here is Newton-Cartan theory. To each Trautmann-gauge orbit of Newtonian gravitation theory, there is a unique model of Newton-Cartan theory. So what do the models of Newton-Cartan theory look like? Well, now they're just 5 tuples. I no longer have the gravitational potential phi, but instead I have a different derivative operator. This still satisfies the compatibility conditions, and I still have the orthogonality condition. But then dynamics are picked out a bit differently. So I have this first equation, which is the geometrized Poisson equation. And then I have 2 curvature conditions, which have natural physical interpretations in terms of the existence of certain time-like vector fields. So this one says that there is a rigid and twist-free vector field, and this one says that there is a geodesic and twist-free vector field. We can go into what that means if people are interested. The most important thing, I guess, for us is this last equation, which says that gravitating but otherwise force-free bodies in Newton-Cartan theory, in fact, do move on geodesics of the connection. In this sense, this is a geometrized version of Newtonian gravitation theory. Great. And now, given a model of Newton-Cartan theory, you can reconstruct up to Trautmann-gauge symmetry a model of Newtonian gravitation theory. And that is the content of the Trautmann recovery theorem. So we've got this map between a force theory of Newtonian gravity, just standard Newtonian gravitation theory on the one hand, and Newton-Cartan theory on the other hand. And this is related, these two theories are related by Trautmann, geometrization, and recovery. Okay, so now on to relativity. So kinematically possible models of general relativity you could take to be picked out by triples M, G, and T. G is a Lorentzian metric field on the manifold M, and T is the stress energy tensor. And these guys are coupled in this, the Einstein field equation, where this is the Einstein tensor associated with the Levi-Civita derivative operator for G. Sorry, there's a Chinook over my house. Okay, and then we also have this equation, which tells us, again, that gravitating but otherwise force-free bodies move on geodesics of the connection. So general relativity, also a geometrized theory of gravity. Okay, so what would be a candidate force theory of gravity, which is equivalent to general relativity, in a similar vein to Newtonian gravitation theory being a force theory which is equivalent to Newton-Cartan theory? The answer is going to be a theory known as teleparallel gravity. But in order to explain this, I need to introduce a bit more formalism. So I need to introduce tetrad fields. So remember that at each point in the manifold in general relativity, we can always find a set of basis vectors which effectively diagonalize the metric. So I've got this equation. So we can define a tetrad field to be a set of 4 vector fields which at each point in the manifold provide an orthonormal basis for the tangent space. Okay, so when I have a tetrad, I can then define a different derivative operator. And this is known as the Weitzenbock derivative operator, which looks like this. And it turns out that this derivative operator has torsion. So going one direction then another doesn't commute. That's the geometrical definition of torsion, but no curvature, unlike in general relativity. So I've traded curvature for torsion. Then using the tetrad and using the Weitzenbock derivative operator, I can write down this theory. Here's how people normally present teleparallel gravity. Obviously not as elegant as general relativity, but it's still a legitimate theory, so we should consider its implications. The most important thing to look at here is the force equation for gravitating but otherwise force-free bodies. One finds that gravitating but otherwise force-free bodies do not move on geodesics of the Weitzenbock connection, but rather they deviate from geodesics in a way which is given by this term on the right-hand side, which is proportional to the torsion of the space-time. Okay, so this procedure where you write down the tetrads, you construct the Weitzenbock derivative operator, and then write down your teleparallel theory is a procedure known as teleparallelization. To my knowledge, it was also first considered by Einstein in the 20s. I know that Dennis Lehmkuhl is doing some work on the history of this. And it degeometrizes general relativity. It turns a geometrized theory into a force theory, just like Troutman recovery degeometrizes Newton-Cartan theory. So there are suggestive analogies with that Newton-Cartan theory, Newtonian gravitation theory relationship. In the philosophy of physics literature, the first person to point to these analogies was again Eleanor Knox. She has a very nice paper from 2011 called Newton-Cartan theory and teleparallel gravity, the force of a formulation, in which she points to these analogies and discusses some of the philosophical consequences or differences between the two. And I'll come back to some of those. And this was kind of the starting point for Nick and me. We wondered whether one could make these things a bit more precise. Maybe the analogies are not merely suggestive, but maybe it is in fact exactly the same thing going on in both cases. Maybe, in other words, one could take Newton-Cartan theory and try and apply the same machinery of teleparallelization and cross one's fingers and hope that one gets Newtonian gravitation theory. That was our starting point. So this is what I want to talk about now, the work that Nick and I did here. So here's a commuting diagram which we drew near the start of our paper. So we know that if we start off with general relativity and we teleparallelize it, we'll get teleparallel gravity. We know that if we have Newton-Cartan theory and apply Troutman recovery, we'll get Newtonian gravitation theory. What we wondered is whether one can teleparallelize Newton-Cartan theory and whether you get the same thing. And it turns out that one does. And that's what I'm going to talk about now. We also looked at things in the vertical direction in the sense of taking a certain kind of Newtonian limit, limit in scare quotes, because this thing null reduction isn't really a limit. But it turns out that this works as well. So I can take the Newtonian limit of general relativity and get Newton-Cartan theory, or I can do the same thing for teleparallel gravity and I'll get Newtonian gravitation theory. So these are a set of nice links to show, I think. I'm in what follows going to be focusing on this left to right direction. Okay, so how does this work? A tiny bit more formalism. So recall that a fiber bundle is a space which has locally the product structure B cross F, where B and F are smooth manifolds, but which globally might have different structure. There's no way to identify elements of the fibers corresponding to infinitesimally close elements of the base space B, absent adding extra structure. To do that, we need to introduce a connection. So how does this look in general relativity? Well, let our base space be the manifold M. The fibers are going to be Minkowski vector spaces. The tetrad provides a map from the tangent space to the corresponding Minkowski vector space. And then to identify elements in a fiber at a point P with an element in a fiber at some point Q, which is infinitesimally close to it, I've got to introduce a connection, which is known as the spin connection. And it's related to the space-time connection via this equation, which is known as the Vielbein hypothesis. Okay, so now I have a tetrad and I have a spin connection in this way of presenting general relativity. I can relate these guys to the torsion and the curvature of the space-time using these equations, which are known as the Cartan structure equations. I plug in my tetrad and my spin connection, and I'll find out what the torsion and the curvature of the space-time is. This provides kind of a next level up understanding of what's going on in the difference between general relativity and teleparallel gravity. So in general relativity, I'm setting the torsion to 0. I'm setting this second Cartan structure equation to 0, but I'm letting the curvature be non-zero. Whereas in teleparallel gravity, I'm doing the opposite. I'm setting the curvature to 0, but I'm letting the torsion be non-zero. That's kind of what is going on geometrically in the difference between these theories in this formalism. All right, so previously I presented teleparallel gravity like this. I wrote the Weitzenbock connection down like this. In fact, that omits the spin connection and historically led proponents or researchers into teleparallel gravity getting into some knotty issues regarding the coupling to spinorial matter. What we need to do to fix this is to go to covariant teleparallel gravity, which has another term, which features the spin connection. And in fact, that falls out naturally from the geometrical formalism, which I had on the previous slide. This is the most general space-time connection, which is consistent with the conditions that the curvature be 0, but the torsion be non-zero. So it kind of makes sense that we should be dealing with this object. Right. There's a very nice Springer book on teleparallel gravity, by the way, which discusses all of this. Okay, so now Nick and I try and carry this over to the Newtonian case. How does one do that? One first needs to define a Newton-Cartan tetrad, or inverse tetrad here. This has 5 components. So first of all, I have the clock one form. Then I have 3 spatial tetrads. In addition, I have this object MA, which is known as a mass gauge field. You might wonder where this comes from. There are a few different ways to motivate it. One is that you need it in order to consistently couple a point particle to a Newton-Cartan background. I can discuss the motivations more if people are interested, but for the time being, I will just use it and we'll see what happens. The spin connection decomposes in the Newtonian case. And by the way, this is not stuff that we did. This is work that people in the physics literature have done over the past 20 years or so. It decomposes into what's known as a rotation connection and a boost connection, which you can just write like this, just different components of the overall spin connection. And then you can recover your standard Newtonian objects in not too difficult a way. So this clock one form is already appearing directly in the tetrad, and I can reconstruct my spatial metric in this way using my spatial tetrads. Okay, so if I take those components of the tetrad and I take those 2 bits of the spin connection, the boost connection and rotation connection, and I plug them into my Cartan structure equations, I'll get 5 equations. So I just go back to the Cartan structure equations. I just imagine plugging in the different bits of the tetrad into this formula for T, say. I get 5 equations. This was worked out by Andringa and collaborators in 2011, and they look like this. So I have 3 equations for torsion and 2 equations for curvature. And I won't go into this, but people end up associating these with the generators of the Bargmann group. which is the central extension of the Galilean group. So this is the generator of Galilean boosts, spatial rotations, temporal translations, spatial translations, and this slightly weird one, mass translations. All right, so once again, that was not us. People had done it before. But now we can just think about trying to do the same thing that people do in the context of GR and teleparallel gravity, but in the Newtonian case. So if you set the torsions to 0, you will recover Newton-Cartan space-time connection, nabla hat. You can ask what would happen if I were to set the curvatures to 0. What would drop out? If I impose those conditions, in fact, the 2 of the torsion equations are already automatically set to 0 as well, which is already telling us that I have 0 space-time torsion. So it's only going to be the mass torsion which is relevant. If I then push through, I'll find that I get this force equation corresponding to the Newton-Cartan geodesic equation. I find that there's a term on the right-hand side which is associated with mass torsion. There's still a little bit of gauge fixing that you can do here, which is associated with the curvature conditions in Newton-Cartan theory, which I've talked about before. In particular, I can use them to go to a twistless gauge, which lets me write the mass field m as some function phi times the clock form t. If I go to that gauge, then I end up with this thing, which is, of course, just the Newtonian gravity force equation. And I can also do the same thing with the Poisson equation, and the Poisson equation will drop out. So moral of the story, by applying the same kind of methodology that people use to understand the difference between GR and TPG in the Newtonian case, you can see that Newtonian gravitation theory just is the teleparallel equivalent of Newton-Cartan theory. And I think it's reasonable, therefore, to say that this generalizes / subsumes the Troutman recovery theorem. It also shows us that this connection between these two, or the analogies between these two links, GR and TPG and Newton-Cartan theory and Newtonian gravitation theory, is more than merely suggestive. It's there's a mathematically precise way of understanding exactly what's going on in each case, and it's the same thing. Okay, so 2 very quick comments on this. I think that we can use this understanding to shed some lights on issues which have been raised in recent papers in the philosophy of physics. So in Eleanor's 2011 paper, for example, she comments on the different status of inertial motion in Newtonian gravitation theory versus teleparallel gravity. And she writes this: the components of the Weitzenbock connection of teleparallel gravity cannot be made to vanish by an appropriate choice of reference frame. That, by the way, is because the connection is torsionful. It seems that the geodesics of the Weitzenbock connection simply don't have full inertial structure associated with them. What she's presumably thinking here is that you need the connection coefficients to vanish in order for point particles to follow Newtonian straight line inertial trajectories. And if you can't get that, then you don't have a full notion of inertial structure. Makes sense to me. But you might ask, given that the GR teleparallel relationship is mathematically analogous to the Newton-Cartan Newtonian gravitation theory relationship, why should it be that the force theory in the former case, teleparallel gravity, admits of no notion of inertial structure, whereas the force theory in the latter case, Newtonian gravitation theory, does admit of a notion of inertial structure? But it seems like there's a pretty straightforward answer now. Though they both have connections with non-zero torsion, it's only in the former case that it's space-time torsion. In the Newton-Cartan or Newtonian gravity, sorry, that should be NGT. It's only in the Newtonian gravity case, or in the Newtonian gravity case, your torsion is mass torsion, not space-time torsion. So you can still define a torsion-less space-time connection, and so you still have a notion of inertial motion in Knox's sense, which seems to wrap up that issue, which might otherwise be puzzling. Another quick thing which I think you can do with this relates to the conventionality of geometry. So just to remind you, Poincaré in 1905 wondered about cases in which the geometrical structure of space-time would be underdetermined by empirical experience. So one had to select a particular space-time geometry as a matter of convention. One way in which you might regard this conventionality of geometry to manifest itself is through the possibility of interconversion between using a framework with a curved derivative operator and no forces versus a flat derivative operator and forces. And this is the kind of thing that Weatherall and Manchak talk about in their 2014 paper. I think that there are legitimate worries about whether this notion of conventionality is the same thing that people at the start of the 20th century had in mind, but let's bracket that as well. So Weatherall and Manchak think about the comparison between general relativity and Newton-Cartan theory here. When they're thinking about Troutman recovery, they write this: does a similar result hold in relativity? The analogous proposal would go as follows: fix a relativistic spacetime and let nabla be the Levi-Civita derivative operator compatible or associated with G. Now consider another torsion-free derivative operator, ... The answer to the question, does a similar relationship result hold, is no. But you can see that they kind of shut off the possibility by fiat here. So teleparallel gravity exploits a loophole in this proof because the derivative operator of the theory is not torsion-free. Once you note that, the situation seems much more parallel. You have analogous cases of conventionality, if you want to regard this as being an issue of conventionality at all, in both the relativistic context and the Newtonian context. Now, I just want to flag here that there might be kind of a second order way of defending what Weatherall and Manchak are claiming. So Eric Curiel made the point to me that Newton-Cartan theory places much more stringent restrictions on the manifold being parallelizable than general relativity does. Parallelizability of the manifold is a necessary condition to get the teleparallel procedure off the ground. And so in that sense, you might think that the conventionality is more ubiquitous in the Newton-Cartan framework than in the general relativity framework. So fair enough, maybe there is a way of thinking that there's something in Weatherall and Manchak's claims, although it's not quite for the reasons that they were indicating. Okay. Okay, so that takes us to the end of the first half of the talk. I've shown that Newtonian gravitation theory is the teleparallel equivalent of Newton-Cartan theory, just like teleparallel gravity is the teleparallel equivalent of general relativity. So now we can turn to equivalence principles. I want to present a framework and classification of equivalence principles, and as I said at the outset, I want it to include the following ingredients. I definitely want it to connect with Lehmkuhl's classification of equivalence principles, which, like I said, seems completely right to me. I also want it to make contact with Knox on Newtonian equivalence principles, since Knox talks about the Newtonian strong equivalence principle. I also would like it to connect with some other interesting recent work in the literature. So Weatherall has a paper from 2011 on deriving the coincidence of gravitational and inertial masses in Newtonian theories. It'd be nice to say something about that, since this coincidence is sometimes regarded as one version of the equivalence principle. It would also be nice to talk about, for example, Greaves and Wallace on deriving Einstein's elevator, which is something which I'll come to. Okay. So whenever we're talking about equivalence principles, the subtleties are endless. And so there are some things which I need to set aside at the outset. I could say more about any of these if people would like. So one is how to define test bodies. This is a notoriously difficult issue. Another is between pointy versus neighborhoodly versions of the strong equivalence principle. So just to anticipate, the strong equivalence principle in general relativity says something like the laws of physics are locally special relativistic. But it's easier to make mathematical sense of that at a point in the manifold versus in the neighborhood. And so justifying the neighborhoodly claim turns out to be quite difficult. This is something that Harvey Brown, Demis, Lehmkuhl, and I talked about in a paper from a few years ago. Another thing that we talk about is what we dubbed the two miracles of general relativity. So the issue here is, why should it be the case that the equations governing all different matter fields simplify in the same coordinate systems? And why should it be the case that that simplification coincides with the simplification of the metric field? In other words, why do the symmetries of all of the dynamical laws coincide locally with the symmetries of the metric field? Yes, I don't take anything that I'm going to say in what follows to be inconsistent with this. Some of my discussion of the strong equivalence principle won't make heavy reference to the dynamics governing matter fields, but you could read it in that way if you wanted to. I don't take anything here to be inconsistent with the claims that Harvey and Dennis and I were making. And relatedly, again, something that we talk about, there are some issues with ambiguity and curvature couplings and second order dynamical equations. I'm not even going to go into that. Okay, so let's start off with the weak equivalence principle. In Lehmkuhl's paper, he presents two versions of this principle, which he calls WEP1 and WEP2. WEP1 reads as follows. It says, if an uncharged body is placed at an event in spacetime and given an initial velocity there, then its subsequent trajectory will be independent of its inertial structure and composition. WEP2 states that for any body, the gravitational mass of that body is equal to its inertial mass. People have thought about the relationships between these two. And as Lehmkuhl says, WEP2 seems to imply WEP1. To see this, suppose that WEP2 holds that gravitational mass is equal to an inertial mass, and consider a body with an inertial mass mi and gravitational mass mg. Its force equation would be this. If it's in a uniform gravitational field and there are no other forces, then the acceleration of this body would just be given by dividing mg by mi. So you get mg over mi ga, where this is the gravitational field. So when this is a constant, if the inertial mass is equal to the gravitational mass, all such bodies would fall at the same rate, independent of their constitution. So it seems like you can derive WEP1 from WEP2 fairly straightforwardly. Okay, so if I now imagine a bunch of bodies which are in a gravitational field, it follows from WEP2 that the motion amongst themselves shouldn't depend upon the strength of that uniform gravitational field. If you then take this to also be true of uniform accelerations, and here we have something like Newton's corollary 6 in the vicinity. This is very nicely discussed in Saunders' 2013 paper. Then you're going to recover what Knox and Stachel call the Einstein equivalence principle. I'm just going to abbreviate that to NEP. And importantly, I was going to say I don't want this to be associated with Newton, but it's also associated with Einstein, so I guess that's fine. I'll just abbreviate it to NEP. This is very close to what Saunders dubs the equivalence principle in his paper. And it says this: no experiment can distinguish between the effects of a homogeneous gravitational field and the inertial effects arising in a uniformly accelerating frame. Good. So at the moment we have that WEP2 implies WEP1. With some extra assumptions, this implies this Einstein equivalence principle. Okay, so next thing, what Lehmkuhl calls the Einstein equivalence principle. This draws on this symmetry in the Einstein equivalence principle, this indistinguishability of uniform gravitational fields and inertial effects arising from an accelerating frame, and uses this to instigate a conceptual unification of gravity and inertia. So Lehmkuhl puts it as follows: gravity and inertia are the same in their very essence. I would like to read this in a bit more mathematical a way. It seems to me that what's going on here is a commitment to a geometrized framework for gravitation. And so I would write it as follows. So gravitational and inertial effects are conceptually unified insofar as both are represented by the components of the same possibly curved compatible connection. Good. So what were two different things, a gravitational force and inertial effects, cease to be different in a framework which embraces the Einstein equivalence principle. There are open questions and discussions to be had about whether the notions of gravity and inertia really even make sense in geometrized theories which embrace the Einstein equivalence principle. And again, some nice discussion of that in Lehmkuhl's paper. Okay, so before we move on to the last kind of equivalence principle, the strong equivalence principle, which, like I said before, in the relativistic context regards the local validity of special relativity, I need to introduce some facts about normal coordinates. So this is all pretty standard. So recall that in a coordinate basis, the connection components associated to a derivative operator, defined in this way. At any point in the manifold, we can choose normal coordinates such that the connection components with their lower indices symmetrized vanish at that point. If the connection is torsion-free, then of course it doesn't have an antisymmetric component in the bottom two indices, and I can just write that the connection components themselves vanish at P. Now, if I take that manifold to be equipped with a Lorentzian metric field, and I use the unique torsion-free compatible derivative operator, then in normal coordinates at P, the first derivatives of the metric will vanish. And then I can choose a subset of the normal coordinates, the confusingly termed orthonormal normal coordinates, where the metric field diagonalizes and looks like the Minkowski metric at a point. Okay, good. So you can already see how this is suggesting something to do with the local validity of special relativity insofar as I'm getting something at a point which looks like the Minkowski metric. So now the strong equivalence principle. This is to be articulated within the context of a completed theory of gravity. Insofar as we're dealing with relativity, completed theory of relativistic gravity, i.e. general relativity. It comes in two versions, though, depending upon whether the Einstein equivalence principle is endorsed. And this is going to be quite important. So first, the Einstein equivalence principle endorsed version of the strong equivalence principle, which I wrote SEP1 subscript, SEP subscript 1 EEP. This says, at any point in the manifold, we can find a normal frame in which gravito-inertial effects, as represented by connection coefficients, are transformed away. As I said before, often the strong equivalence principle is written in terms of locally the dynamical equations taking their simplest form in such and such coordinates. That could be rendered consistent with this. If I take dynamical equations for matter and I say that they're coupled to the Lorentzian metric and they use the Levi-Civita derivative operator, then these frames, these normal frames, will be the frames in which the dynamical equations for matter take their simplest form. Great, so that's the geometrized version. But we also have a degeometrized version, i.e. SEP1, but where EEP is not endorsed. And this takes it to slightly different form. This says at any point in the manifold, one can find a frame in which inertial effects, as represented by connection coefficients, cancel gravitational effects as represented by some tensorial quantity. So I've gone to the frame in which gravitational effects do not appear to be there. That need not be a normal frame in the using the derivative operator for whatever theory is under consideration, but that will become a bit clearer in a second. You can also think about the classes of frames in which this principle holds. So it doesn't necessarily just hold in one. The normal frames might be related by certain kinds of coordinate transformations. So I here write SEP2 EEP and SEP2 not EEP. These say respectively the following. The first says that SEP1 EEP holds and the frames in which this principle holds are related by Lorentz transformations. By the way, another caveat is that I'm setting aside local translations. I think that there are ways to make sense of this, but I'm just going to set those aside. Again, we can talk about it in the Q&A if people want. On the other hand, we've got SEP2 not EEP, which states that SEP1 not EEP holds, and the frames in which this principle holds are related by Lorentz transformations. If you're thinking about this geometrically, then in the case of Lorentzian manifolds, the Lorentz symmetries, which we're talking about here, are inherited from the killing symmetries of the Minkowski tangent space using the exponential map construction. I know that an advocate of a dynamical view like Brown might not like that way of appealing to geometrical facts to explain something about the laws. I don't think it's so bad in light of how things are presented in the last chapter of physical relativity. Harvey and I were talking about this earlier this week, and maybe this will come up as well. Okay, so let me summarize this framework. So the weak equivalence principle 2 implies WP1, which in turn implies NEP when combined with certain other assumptions. The EEP provides a conceptual unification of gravity and inertia. SEP1 regards the local transforming away of gravitational effects, and this can be read in two different ways depending upon whether the EEP is also endorsed. And SEP2 regards the transformations which relate such coordinate systems. Good, so that was mostly phrased in the relativistic case, but note that in fact there was nothing really relativistic about any of these guys. There was no explicit commitment to either a relativistic or a Newtonian framework. So it's only at the level of the strong equivalence principle that there could be any difference between the relativistic and Newtonian equivalence principles. So let's think about Newtonian equivalence principles a bit more now. So here's how Knox writes the Newtonian equivalence principle in her 2014 paper. She writes this. I deleted some stuff which isn't important for us at the start regarding to any degree of approximation here. But let's just read it as follows. So in the neighborhood of any P in M, it is possible to find a reference frame with respect to whose associated coordinates the motions of bodies amongst themselves are indistinguishable from those expected in the absence of external forces. When you look at this, it seems to me most natural to read it in the de-geometrized way, the cancelling of gravitational effects on making a judicious choice of frame. I guess first point is that it would also be possible to articulate the geometrized version of the strong equivalence principle in the Newtonian case. This would simply be a statement of the existence of normal coordinates in Newton-Cartan theory, which we know to exist since the derivative operator is torsion-free. What would SEP2 be in this case? Well, this set of coordinates will inherit the flat space-time killing symmetries of the tangent space. And so these coordinate systems will be related now not by Lorentz transformations, but by Galilean transformations. And so that's really the only difference between the Newtonian case and the relativistic case, the frames in which one has these particular systems. This simplification. So you could write in the Newtonian case, SEP2 EEP states that SEP1 EEP holds, and the frames in which this principle holds are related by Galilean transformations. And the de-geometrized one says SEP1 not EEP holds, and the frames in which this principle holds are related by Galilean transformations. Okay. So now let's just try and make this a bit more precise using the stuff from the first half of the talk. I'm going to focus just on particle force equations for simplicity. So in general relativity, you can write the Newtonian, you can write the geodesic equation like this in a coordinate basis. In normal coordinate systems, we already said that connection coefficients vanish. So that would be SEP1 EEP. And these frames are going to be related by Lorentz transformation. So that's SEP2 EEP. What about teleparallel gravity? Well, if I were to write the TPG force equation in a coordinate system, I would have this, where I have my coordinate derivative operator here, and then some connection coefficient terms associated with the Weitzenbock derivative operator, and then a torsion term on the right-hand side, which is representing the gravitational force. I can choose my frame such that the connection coefficients cancel the gravitational force as given by this torsion. And so, yeah, this amounts to choosing a frame such that inertial effects are cancelling the universal gravitational force. The difference between the Levi-Civita derivative operator and the Weitzenbock derivative operator is known as the contortion tensor, which is very closely related to the torsion tensor. It just involves swapping indices around a bit. And you can show, therefore, choosing this frame, that this will amount to choosing the frame in which the Levi-Civita connection coefficients vanish. We've shown that the frames which relate, the frames in which the Levi-Civita connection coefficients vanish just are well, are related by Lorentz transformations. So this should hold in the teleparallel case as well. The frames in which I get this cancellation are related by Lorentz transformations. And that would be the degeometrized version of SEP2. What about the Newtonian case? In Newton-Cartan theory, again, you can write the geodesic equation as this. In normal coordinates, this term will vanish and you'll get SEP1 EEP. The frames in which this is the case will be related by Galilean transformations, which would be SEP2 EEP. What about Newtonian gravity? There I would write the force equation like this. I can choose a frame such that these Newtonian Weitzenbock connection coefficients cancel the term on the right-hand side, which we now know to be related to mass torsion, which would be SEP1 EEP. I can make a choice of frames such that the gravitational effects are transformed away. And then in the teleparallel interpretation, as I said, this involves choosing a frame such that inertial effects cancel mass torsion. And then we know from Trautmann recovery that this choice amounts to setting the Newton-Cartan connection coefficients to vanish. So that should tell us that the frames in which this is the case are related by Galilean transformations. I just want to comment on one thing. On the one hand, we have internal symmetries or gauge symmetries in the degeometrized models. And on the other hand, we have the frames in which this nice cancellation takes place. In the relativistic context, there is in teleparallel gravity, and this isn't something that I mentioned before, there's a internal gauge freedom, a freedom to choose your tetrads in any way such that they are related by internal Lorentz transformations. And so we've got this internal Lorentz gauge freedom. These symmetries coincide with the symmetries in which you have the frames in which the strong equivalence principle holds. And that's no surprise since these are both inherited from the symmetries of the tangent space. In Newtonian gravity, the gauge symmetry of the recovered models is the Trautmann symmetry, which now doesn't coincide with the Galilean symmetry in which I get this fortuitous cancellation. The reason for that is that the Trautmann symmetry involves this extra object, the mass gauge field. And so we shouldn't expect it necessarily to coincide with the symmetries in which I have this cancellation between the gravitational effects and the inertial effects. But if I stipulate that the gravitational potential is constant, or at most can change only by a constant shift, which normally is not regarded as being physical, then your residual Trautmann symmetry coincides with the familiar Galilean transformations. And so, okay, bringing all of this together, one gets a map of equivalence principles, which looks something like this. So this is all from Lehmkuhl. So we have the WEP2 implies WEP1. And then we said that if I impose corollary 6-like assumptions, I'll get the Newtonian equivalence principle. I know that these stronger versions of the strong equivalence principle, which talk about the frames in which I get cancellations of gravito inertial effects, or the frames in which the connection coefficients vanish, hold, imply the weaker ones just because they are strictly logically stronger claims. And so I should have arrows going this way. I've got these bidirectional arrows here, which relate to geometrization and recovery. I know that SEP1 implies EEP, again, just because it contains a commitment to EEP in its presentation. This one, I guess you can take or leave. So this is the claim that the Einstein equivalence principle implies that gravitational effects are indistinguishable from inertial effects. On the one hand, that seems obviously true. If they're conceptually identified, then of course they're indistinguishable. But on the other hand, you might think that's a bit fishy because you can't really make sense of the notion of gravitation or inertia in themselves in a geometrized framework. And so I guess you could take or leave this arrow. Which leaves one outstanding, which is this one from the degeometrized version of the strong equivalence principle to the weak equivalence principle, the coincidence of gravitational and inertial masses. What to make of this link? Well, actually, it's something which is discussed by Weatherall in a 2011 paper. So working in a degeometrized theory. He gets the degeometrized force equation, but with no masses on either side. He then just multiplies through by the inertial mass and says, look, obviously this yields the coincidence of gravitational and inertial masses, i.e. WEP2. So that seems to show that once you're in a degeometrized framework, you can get this coincidence. If you got that degeometrized framework from recovery applied to the geometrized theory. So Weatherall claims to derive the second version of the weak equivalence principle in Newtonian gravity via a two-step process, first taking the Newtonian limit of GR to arrive at Newton-Cartan theory, and then degeometrizing Newton-Cartan theory using Troutman recovery to arrive at the force equation of a recovered model. In our language, this would involve beginning with SEP1 EEP, i.e. a geometrized theory, moving to the same principle in the Newtonian case by taking the Newtonian limit, and then degeometrizing to arrive at the degeometrized theory, i.e. Newtonian gravity, and then deriving the coincidence of gravitational and inertial masses from that. Once one has these parallels between the relativistic framework and the Newtonian framework in mind, it seems like there would be another way of getting Weatherall's result. Just degeometrize general relativity to arrive at teleparallel gravity and then take the Newtonian limit. Another way of getting the same thing. Another quick thing is that Weatherall's derivation of WEP2 relied on starting with a geometrized theory and then degeometrizing, so it's kind of an intertheoretic derivation of an equivalence principle. I just want to flag that this is kind of different from some intratheoretic derivations of equivalence principles. So for example, in 2014, Greaves and Wallace consider a subsystem environment decomposition in Newtonian gravity and are able to derive something like the Newtonian equivalence principle, the indistinguishability of gravitational and inertial effects, i.e. Einstein's elevator. Okay, so now let me make some comments on how Lehmkuhl presents the importance of some of these principles as bridge principles between general relativity and other theories, and see if I can say a little more about that. So for Lehmkuhl, SEP2 EEP, that locally you're getting physics which maximally simplifies in coordinate systems related by Lorentz transformations, is a bridge principle which links general relativity to special relativity. On the other hand, Einstein's equivalence principle is a bridge principle linking general relativity, in which individually the notions of gravity and inertia don't really make sense anymore, to Newtonian gravity, in which they do make sense. On the former, I guess what I want to say is generalizing beyond the Newtonian context, what SEP2 EEP is doing is linking a geometrized theory to the local tangent space symmetries of that theory. On the latter, the Einstein equivalence principle is expressing a commitment to a geometrized space-time setting. So maybe, although I think it's completely right to understand the Einstein equivalence principle for Einstein as being a link from GR to Newtonian gravity, maybe the thing that we should say these days is that it links not general relativity directly to Newtonian gravity, but rather to teleparallel gravity, its equivalent force theory, and then only via taking some kind of Newtonian limit to Newtonian gravitation theory. I don't take this to be disagreeing with Lehmkuhl, really, just nuancing it a bit. Okay, so here's what I have done today, and I'm really looking forward to discussing. So I've presented a web of equivalence principles, which with recovery as teleparallelization in mind is equally applicable to both the Newtonian and relativistic contexts. And I hope that this incorporates the work by Lehmkuhl and Knox on these issues, and I hope that it's also compatible with these things by Weatherall and Greaves and Wallace. Great, so yeah, thanks a lot.
Brilliant, thank you. We could do questions via just writing hand or finger or something in the chat box. Let's do grad students first. So if you have a question and you're a grad student, write hand in brackets grad or something.
Are you forgoing the Oxford customary break?
Oh yeah, let's have a break. Sure, let's have a.
I don't mind.
2-minute break. Yeah,
Okay.
5:30. Let's come back. Okay, great. Great. Are you ready to go, James?
Yes.
People have had their break. Are there questions? Leah.
Hi, James. Yeah, thank you so much. That was a really interesting talk. So I just had a question for clarification about you made a very short comment about the conventionality question between different geometries, and you can't distinguish, or different spacetimes, I guess, and you can't structures, and you can't distinguish between them.
Yeah.
And you said something very quickly about the ability to do this kind of teleparallel procedure.
Yeah.
And what kind of restrictions that puts on your theory. And I was wondering if you could say a bit more about that, because it sounded.
Yeah, so this is something that came up in conversation with Eric, like I said. So Eric made the correct point, which is that to be able to teleparallelize a theory, you need the manifold to be parallelizable. You need to have a basis of vector fields. Then the claim was that in general relativity, we have non-parallelizable manifolds. So not all of the models of general relativity will have a teleparallel equivalent. The following is the thing that I don't completely understand. Maybe it's obvious and I just haven't thought about it hard enough. But the claim then is that in Newton-Cartan theory, you need the manifold to be parallelizable. And so every model of Newton-Cartan theory presupposes a parallelizable manifold. Which would mean, in a certain sense, the issue of conventionality as given by teleparallel gravity looms larger in the Newtonian context than in the relativistic context.
Because in the relativistic context, you would consider a broader class of structures, and basically.
Yeah. So you'd only get the conventionality in this sense for those models of GR which are on a parallelizable manifold.
Right. But in the other case, that you're kind of given that anyway. Okay. Yeah, that was my question.
Cool.
Thank you.
Okay, so if you're a student and at some point in the question period you have a question, then write it and we can put you to front of the queue. Otherwise, too sharp.
Great, thanks, Alex. Thanks a lot, James. That was fantastic. We've spoken about this a lot. We'll continue to speak about this a lot. But I have a question specifically about your hang on, I can't see. Oh, there we go. Sorry. I have a question specifically about your SEP2 EEP.
Yeah.
And the sense in which that's putatively recovering this notion of the local validity of special relativity. And sort of the specific question is something like this. If according to SEP2 EEP, the transformations between the locally privileged frames are Lorentz transformations, then what that's effectively saying is if I go to a sufficiently small region, then my privileged frames will be related by Lorentz transformations. But that doesn't uniquely give you that it's going to be locally Poincare invariant, because it could also be locally constant curvature de Sitter or constant curvature anti-de Sitter. And those will also be preserved by Lorentz transformations. Those privileged frames will also be preserved by Lorentz transformations. So then it seems like either SEP2 EEP is mischaracterizing special relativity by saying if it captures the notion that GR reduces to SR, then SR should also include constant curvature de Sitter, anti-de Sitter, and Poincare as possible models, or it's not capturing this notion of GR locally reducing to SR. So yeah, I guess my question is what's happening over there?
So there's a few things which come to mind. So, I mean, at least you can say it captures the local validity of an important aspect of SR.
Yeah.
That's really cheap. I guess another thing which comes to mind is this Sam Fletcher paper, which we've talked about a bit. So local Poincare symmetries. I mean,
Yeah.
I mean, do you think that helps? Not really, right? Because it doesn't break the symmetry between. It just says you could define local Poincare symmetries.
Yeah. Yeah. I mean, I think this is part of a sort of more general concern about the SEP. And so in a sense, this kind of floats freely a little bit from much of what you said in the talk, because you kind of took this to be capturing that notion. And so I guess my question is, yeah, I mean, nothing about sort of the setup in your talk really changes, except maybe the claim that there's a sort of precise sense through the SEP, through SEP2, in which you can talk about SR as conceived of as a Poincare invariant, globally Poincare invariant theory, and GR.
I think that sounds right to me. And obviously you can do what we've been trying to do, and which I believe that you talked about earlier today.
Yeah. Yes, but yeah, watch this space. We'll talk about it later. Great. Thanks a lot, James.
David's next.
Yes, thank you. There's lots I could ask. Let me pick one thing and get back in the queue. So I have a standing worry in these situations about trying to characterize the equivalence principle in gravitating theories in a way which doesn't do sufficient justice to self-gravity.
Okay, yes.
So we want it to be the case that the equivalence principle applies to the Earth-Moon system. We want to be able to say things like, the reason why we can ignore the effect of the sun's gravity while studying the Earth-Moon system is because solar tidal forces are small over the scale of the Earth-Moon system. Therefore, we can treat the gravitational effect essentially constant. Therefore, the equivalence principle, blah, blah, blah. But it's going to be somewhat tricky to apply these definitions on an ultra-local scale if we want to handle strong gravity. It's going to be kind of tricky in a Newtonian or Newton-Cartan situation. It's going to be horribly tricky in GR in a situation of strong gravity where we might have like a binary black hole system or something like that. So just let me just put this fairly open-ended question: how are you thinking about the equivalence principle for self-gravitating systems in the context of this setup?
So I think it's completely right to not think that the point-wise stuff that we've talked about today is going to be sufficient to characterize all notions of the equivalence principle that one might be interested in. One thing that Nick and I have started talking about is applying a nice paper by Graller and Wald to some of the work that you've been doing, where they provide some formalism for thinking about an observer being so far away from a system such that the system looks infinitely small, or looks like it's at a point. And then I think that one would draw at least a bridge between what I've said today and the kinds of stuff in your other papers. That might not be the whole story. And
that makes sense. And my work on this is shockingly unrigorous, so it cries out for that kind of attention.
Yeah.
Adam?
Thank you very much. So this is a very naive question, Great James. But it just occurred to me that when one starts with, let's say, normal Newtonian gravity, the lesson is that one can geometrize it in two directions depending on what you do to the connection. So you can either sort of make the connection have curvature, or you can give it torsion.
Mm-hmm.
So you would expect, as it were, three theories rather than two. But you seem to identify teleparallelization with degeometrization. And I just wondered what the reason for that is. You know, why not instead say that we've got three theories that have these relations of equivalence, and two of them are geometrized, but rival geometrizations, and one of them is degeometrized.
Maybe this is just an issue of nomenclature, where people take geometrized theories to be the ones in which gravitating but otherwise force-free particles move on geodesics. I don't know if that's sufficient to resolve this issue. So by the way, just to check, so the three theories, are you thinking about one with both curvature and torsion as well?
No, sorry, I'm thinking of one theory in which all of the gravitational behavior is due to a gravitational potential. That's the degeometrized theory. Then you've got Newton-Cartan theory.
Yeah.
And then you've got teleparallel Newton-Cartan.
Right.
And that teleparallel version of Newton-Cartan is a rival way to geometrize gravity, in the sense that all of the action is in the connection, but it's in the torsion of the connection rather than the curvature.
But that third one is also mathematically equivalent to the first one, right?
Well, aren't they all mathematically equivalent?
Oh yeah, I guess so. But like literally the same.
I think that's what I wasn't sure about, and especially in the case of GR, that I would have thought the sort of geometrized analog for GR would be something more like what Weitzenbock had in mind, where you have a split. You know, you have you take the metric field and you split it into a Minkowski part and a sort of a potential like term, and then you end up, your geodesic equation, I think, is quartic in the velocities or something like that.
Okay. Yeah, so I mean, the way that I was thinking about it is that start with Newton-Cartan theory, the degeometrized version literally is standard Newtonian gravitation theory with potentials.
There seemed to be a crucial identification of the torsion acting on the mass and the potential. So that, I mean, that's a strikes me as, I mean, it might be a very easy and simple assumption, but that's the one that makes the link. And
so are you thinking of some like hyper-intentional distinction where you can read this guy as torsion of a more abstract space-time or as a potential?
No, I was just naively thinking that if it's in the connection, then it's geometrized.
Right. Then I agree with that statement. I mean, yeah, you are right that in the relativistic case, potential versions, insofar as they make sense, are not the same as teleparallel gravity. So there seems to be an interesting difference there between the Newtonian context and the relativistic one. Yeah.
Thank you. That's really, really helpful.
Oliver's next, and then Simon, and then David again, unless someone else steps in.
Thanks very much, James. So can I ask you about the little commutative, well, not the commutative diagram, the diagram where you've got them all, the links between them.
Like this one.
Yeah.
Yeah.
So what I'm trying to get it clear on is that naively you might think that you've got a bunch of principles that can be applied in any given space-time theory setting, and a theory may satisfy some but not all of them, and the weak strong nomenclature suggests that kind of thing, the weak one being more easily satisfiable by a theory than the strong. But I take it that that's not the picture that we end up with at all, and it seems that we've got a bunch of principles that are appropriate for a non-geometrized theory, so the ones on the top, and then a bunch of principles that are appropriate for a geometrized theory, namely the ones on the bottom apart from NEP.
Yeah, these ones, yeah.
And then there's a claim that if the one on the top holds in a certain kind of non-geometrized theory, then the one on the bottom will hold in the geometrized theory.
Yes.
because these theories are appropriately dual to one another.
Yes.
And you can use the duality to argue that if the one principle holds in the one theory, it holds in the other. Is that the picture?
Yeah, I think that's right. So first of all, yeah, I'm proposing that with respect to any one given theory, there's actually 3 classifications that you could apply to any particular equivalence principle. Holds, doesn't make sense. That seems, so I completely agree with that first point. I also agree that, I mean, there's a sense in which this diagram is maybe condensing too much stuff, because one is moving from one theory here to, as you said, an equivalent theory here, whereas in this case, one is thinking about, if this principle holds in one theory, does this principle hold in the same theory? So there's a certain amount of detail which is washed out there. But I still...
So what?
Sorry, go on.
Okay. Sorry, go ahead.
I was pretty much done. But so
yeah.
I think I agree with everything you said, but tell me if you don't think that's right.
Well, so, I mean, it's confirming something that wasn't clear to me the first time it got introduced, but when you introduced the SEP1 and SEP2, it was clear that they are kind of analogues of the ones at the top are analogues of the ones at the bottom, appropriate for a teleparallel type case.
Yeah.
Whereas when WEP2 is introduced, that immediately equally looks, you know, unintelligible from a modern geometrical perspective. You know, what is this big GA on the right hand side?
Yes, I totally agree.
And putting it where you put it.
Yes, maybe I need to add some colors to this diagram of the theories for which they're appropriate or something. Thanks.
Simon is next.
Yeah, hi, James. Brilliant lecture, learned a lot from it, but just an elementary comment really. The physical basis of the what you were calling a mass, I think, a field, and the torsion associated with it was not at all clear, and surely was relevant just to the couple of questions back from Adam, that you know, in what sense is the teleparallelized version equivalent to the usual Newtonian version with potential when you're ending up with this torsion? So, but is the torsion that concerns only this? Tell me more, what is this mass?
Okay, so I think I said very briefly that the central extension of the Galilean group is the Bergman group, which involves this extra generator of mass translations. And you might very reasonably ask, where does this come from and why is it physically motivated? There are several different angles to thinking that it's appropriate or reasonable to work with the Bergman group. The one that I mentioned is that if you take a free non-relativistic particle and you write down its action, and then you think about variations, you can you'll end up finding that your conserved charges in fact need to be modified, and they need to be modified such that you get this extra term in the Poisson brackets of the generators. You get like an M on the right hand side. Basically, to actually consistently use this, you need to work with a mass gauge field. That doesn't actually explicitly tell you what this represents, I agree, but I guess it's the motivation for using this formalism.
Well, the motivation becomes the motivation for using the Bergman group and seeking
right, yeah,
to the central extension. But of course, the same thing does happen in classical Galilean field theory. There also a similar. I've never understood whether I've understood it or not. You know, one of those things that you think you might be, you know, getting, but somehow the central extension is important to that too, and the introduction to the mixed parameter comes about in that way.
Right.
Have you looked at those connections?
I haven't actually, but that's a very good point.
Under and Sudashan, that's sort of a treatment of.
Okay. Yeah, that seems like a really important thing to look at. So yeah, we can understand at least mathematically why we use this object, but I agree that there are open questions about the right physical interpretation of it.
I mean, can I, maybe this is a total red herring, but let me just throw it in. I mean, there was a similar peculiar feature to the construction of Joy Christian of a diffeomorphism covariant quantum gravity. I don't know whether you've ever taken a look at that, but he also introduced a certain kind of scalar field, which was a little bit, you know, DS6 machinery or something that was essential to get the whole thing to work.
I haven't looked at that.
Yeah,
I've looked at Joy Christian's work in one context, which is relevant to this, which is him claiming to write down an action for Newton-Cartan theory. That thing is absolutely hideous, and I think that there's been some nice work in the recent physics literature about doing it better. But I take it that that's tangential work, not directly connected with what you're mentioning.
I don't think it was appeared in the quantum mechanical work that he did.
Yeah, sure, okay. But yeah, I should really look at this stuff that you bring up. Thanks.
Nick has a finger on this.
Hi, just really quickly, James, and quick comment on Simon's question. As James said, there's many ways of motivating the mass gauge field. Let me comment on one other way that James hasn't mentioned, and I'll say something small expanding on the way that he did mention. So from the perspective of Newton-Cartan theory, anytime, Newtonian Newton-Cartan theory, I mean, right? This is not arbitrary Newton-Cartan theory in the sense that we have certain curvature conditions that are placed on the theory. One of those curvature conditions ensures that the kind of potential you get out of the theory is a conservative potential. This is what people sometimes call the Newtonian condition. Now, anytime you have a flat Newton-Cartan spacetime, you can write this Newtonian curvature condition as df equals to 0. And then by Poincaré's lemma, f equals to dA. That A is the mass gauge field. So what this is telling us is that locally, this kind of object always exists by Poincaré's lemma. Now, the second way of motivating it, which James already mentioned, I'll expand on briefly, is that anytime you have a set of symmetries and that you want to bring to bear in a physical problem, you try to represent these symmetries on a phase space, or on Hilbert space, on whatever your state space is. Now, if you try to naively represent the Galilean symmetries on phase space, as James mentioned, you will find that actually you can't make all the brackets be consistent unless you introduce this central extension. You have to move to a projective representation of the Galilean group, and this is precisely the Bhagman group.
I mean, I feel like coming back and asking, but is that really an explanation of how mass arises in that context? Is that?
Oh, no, sorry, right. Yes, so there's the other question of what's the relationship between mass and mass gauge, the mass gauge field. And I think the quick answer to that, which hasn't been sufficiently understood, is that from the Hamilton perspective, mass is a conserved charge. And in order to have this conserved charge in a theory, you need the mass gauge field, along with certain integrability conditions. So, for instance, what is going to make the difference between the infinite homogeneous universe, in which case we know that ordinary Newtonian gravity isn't sufficient, and we know that Newton-Cartan theory is a good theory of that, right? What makes a difference is that in this case there isn't a well-defined conserved mass charge, which can be defined for an isolated system. And the integration of the mass gauge field is what quantifies that mass charge.
Yeah, well, just as a side comment, Newton-Cartan infinite mass distribution subject to certain symmetries or boundary conditions. I mean, this relates more to David's recent work on this.
Yeah, I don't have more to say on that, but I also don't want to hijack the Q&A. So I'll finish the comment.
I could at some point show you more about this so-called Newton-Coriolis 2 form vanishing. It's kind of messy, so I'm not sure it's worth doing it now.
Well, David's in the queue again, so David.
Thank you. This is a relatively minor thing, actually, on the just on the way you characterize kinematically dynamically possible models in the early part of the slide, part of the talk. And would you mind getting back to that slide? Just.
Oops. Sorry. Wait.
Yeah. So I mean, what you're doing is obviously absolutely standard in the literature. There's something I'm nervous about. I think some significance here that goes more broadly. The way these rules characterize is we sort of take the matter fields as background. So we distinguish the kinematic from dynamically possible models by saying the gravitational field must satisfy Poisson's equation or the Einstein field equations or whatever. And then entirely, and then our object rho, which is representing the matter fields, or our T mu nu, which is representing matter fields, is just stipulated. It's not dynamically bound in any sense. It's just a given thing. And then separately, we have the test particles, which are stipulated to obey the geodesic equations or what have you. But there's something, from a dynamical point of view, from a sort of, channeling Harvey a bit here, there's something a little odd about that way of setting it up. And what you most naturally imagine wanting to write down is I've got my gravitational dynamics and then some placeholder dynamics for matter fields. And particularly in the context of thinking about the equivalence principle, I wonder if it matters that one sets it up this way with the test particles and with the background matter fields. It looks like back reaction is going to be slightly strange there. It's going to have to be handled sort of by hand.
Sorry, just to make sure I understand. So if I'm doing this in GR, I have like this triple. And one thing that I think is maybe a bit fishy is that this washes out detail of the particular matter fields. That's I guess, one point. And then another is, And then I guess another is, should one include the Z in these kinematically possible models? Are either of these, am I missing? Sorry, I might not be.
No, I mean, we're close, but it's not exactly what I had in mind. I mean, I'm not concerned so much that one's washing out the details exactly. I'm just concerned that there's no distinction here between matter fields that do, or there's very, very little distinction here between matter that does and doesn't satisfy the dynamic equations. So, I mean, formally speaking, I've got two objects here representing mass. I've got T, whose job it is to represent that mass, which is the source of the gravitational field. And I've got I can remember how to pronounce that Greek letter, the C or whatever, that's representing how the matter responds to the gravitational field. But these aren't connected in any way. Effectively, I've sort of got two sorts of matter. One is one ignores gravity and just generates it, and the other is ignored by gravity and just responds to it.
Yeah. So, do you think that these concerns, and I think I shared them, do you think that they are resolved by Garroch-Yang geodesic theorem type results or Garroch-Ehlers?
It probably helps. I'm not sure. Although, I mean, even in that context, I worry that the content of the equivalence principle is not going to be entirely captured by claims about geodesics. I mean, if I've got something like, if my matter field is a Klein-Gordon field or something, I want the Klein-Gordon equation to just, again, in Eleanor terms, I want the Klein-Gordon equation to take the same form, a particularly simple form in any inertial reference frame.
Right.
And I just wonder if there are some advantages in seeing how this plays through if one has a schematic or placeholder description of the matter dynamics and not just the test particle plus background matter way of doing it.
So what I was naively thinking is that some of this this should go through for matter field equations as well, where you'd have the connection coefficients when you write it in a coordinate basis and they will vanish in certain set of frames.
Yeah, I suspect they probably do. I suspect that's right, but I don't know, it's not immediate to me.
Yeah, okay, fine.
I mean, essentially, if you look at the way I was doing it in the material on this, then that was the reason for just putting in a dust equation. Now, dust is not perfectly general, obviously, but so that's a disadvantage from that point of view. But well, let me just leave it there.
Well, I think the point is well taken. Agreed.
Oliver has a finger and a hand. You're going to both.
Well, I was just going to say dust, so that was my finger.
Do you want to take that?
Yes, please. So can I push the sort of anti-Harvey line about SEP 1 and 2 EEP?
Yes.
So you might think that you've got the direction going from right to left as a kind of simple, conjunction elimination entailment.
Sorry, going from SEP2 to SEP1.
Yeah.
Yeah. Okay.
And you might think that you could go in the other direction just by saying, well, the geometrical object that's defining our theory is a Lorentzian metric field.
Mm-hmm.
And that's going to give you that the coordinate systems that are relating these things are related by Lorentz transformations locally. Yes. At a point, or transformations that at a point coincide with Lorentz transformations. And can't you see these principles as trivial from the point of view of the geometrical approach? So from the point of view of the dynamical approach, you've got a number of miracles. You've got the coincidence of various matter symmetries, and then you've got the coincidence of the matter symmetries with the geometrical symmetry. And if all that's in place, then you can state this nice happy coincidence in this way. But if your starting point is I've got a theory involving these objects, one of which is a Lorentzian metric, then SEP1 and SEP2 in this form fall out.
Yep.
Now, of course, it may be that there's curvature coupling that we don't have, in which case the physics is going to look different from point to point, but it's still going to be true that in the special coordinates you get, the thought is that as you stated it, these two principles are still going to be true even if you have, coupling to the Riemann curvature, say, yeah. sorry, the Ricci curvature popping up in your equations as they hold a point in a orthonormal set of coordinates.
So, I mean, if you're stipulating that you're working with a Lorentzian metric and you're stipulating that all matter couples to that metric and the Levi-Civita derivative operator of that metric, then I can see that there's a trivially true, modulo possibly stuff related to what David just said. But I think that there are still outstanding questions for that way of thinking, like why are the couplings as they are? I know it's just by stipulation that that's the only thing that you're interested in. Once you made the stipulations, it's trivial. But I mean, this is the sense in which I claimed that I don't think that this kind of proponent of the geometrical view can avoid what Harvey and I called the miracles. It's just that they now come in at, why did you stipulate that you were interested in such and such equations?
So, I mean, you do some empirical investigation and come up with equations that seem to be satisfied by the world, and it leads you to believe in structure in the world represented by a Lorentzian metric field.
Okay.
And of course, the world might have been such that other objects existed and the physics looks different, but it's not miraculous that our physics is that it is, and not like in these other worlds. But for the dynamical approach, you've got this kind of matter dynamics that you allege you can make sense of independently of there being a primitive Lorentzian metric field somehow, and another one. And then it is, an interesting fact about the world that their symmetries coincide. And there's this other Lorentzian metric field hanging around, which just happens to slot nicely into the slot you can define using these two matter fields symmetries. And so again, that's a nice happy coincidence for you.
But wouldn't you say that for the advocate of the geometrical view, it is at least unexplained why we are in the world that we are in, where everything couples to the Lorentzian metric field, rather than another one in which some matter couples to some objects and other matter couples to other one, even if all of that is construed as, all of that structure is construed in an ontologically autonomous way. I mean, that's the sense in which I think there's still something.
Yeah, so why don't we live in a biometric world?
Yeah. I mean, do you know what the answer would be? I've always wondered about.
No, but I don't think it's it's not miraculous that we don't.
Okay.
Okay, so I'd encourage other people to ask questions as well, but David, we're back with you.
Yes, please do cut across to me. Yeah, I mean, this is sort of relates to some of Simon's work. So one interesting thing about the way this is set up is you're using the connection to and various features of how the connection coefficients of things used to characterize things. And I think one of the details I wasn't entirely clear on the presentation, that's my fault for losing track of it, is what's the level of generality of that? I have in mind in particular something like Simon's version of Newtonian gravity, where the theory doesn't require any connection at all beyond something that will impose a rotation standard to characterize the theory, albeit arguably there is nonetheless a connection definable in terms of the theory's dynamics. And I'm wondering how a theory like that looks in your framework.
So is this, I take it that you're asking more than just what does Simon's theory look like in the formalism of differential geometry?
Yeah, I mean, I know what it looks like in that context, but what it looks like is a thing with an awful lot of gauge freedom and no need in its formalization to be to involve any connection at all. So it's going to look something like I've got an absolute temporal metric, an absolute spatial metric. I've defined a rotation standard in any of a number of ways. It might be convenient to do it. You can do it as a equivalence class of connections, but it might, for these purposes, it might be convenient just to do it with no connections at all. And then, so there's nothing in the sort of explicit angle bracket formalism that says here is the connection. Let's talk about it. On the other hand, there are meaningful questions we can ask about the equivalence principle in that context. And I have kind of guesses as to how I take the framework and apply it. And I certainly don't see that it needn't be applicable, but I'm interested how it would work out.
Presumably, though, one can't make sense of the strong equivalence principles in that framework. Or do you think that one can?
I'm not immediately sure. I mean, one response would be, and then along the lines of Ellen and Harvey, one response would be, well, which mathematical object counts as the connection is not something that can be determined just by looking at its geometrical features, or even whether it exists in the fundamental formalism, but whether the dynamical characterization of the system lets you define a thing that has the right kind of connection properties. But that's going to be a little fiddly to apply in your framework because some of those properties that are supposedly constitutive of something being a connection are the things that your framework's sort of individuating between. So again, I'm not sure I know what the answers are here. I'm just sort of interested in. Yes.
So it seems like one can do everything that I want to do when you have a connection, but when you don't, I'm not sure I can say something too useful now, apart from that. I agree that one should be able to make sense of some notions of the equivalence principle, but this is probably not the right formalism to be thinking about it.
Okay, I mean, that's fair. I mean, I suppose the interesting thing about Simon's case, as compared to some of the biometric theories that Ollie was talking about, for instance, is or that Eleanor talks about in her work on emergence, the biometric cases, I have an embarrassment of connections. I have multiple connections. I can ask, they're incompatible. I can ask questions about which one has geometric significance, and I could do things like work out which thing has which thing satisfies appropriate equivalence principles, and if you're feeling inclined towards something like the around the Knox program, you can start saying that's why that connection and not this connection is the one that counts as the spatial connection. In Simon's theory, you haven't got it's the other way around. You have no explicitly stated connection at all, and yet you have in Harvey Eleanor terms, you have a notion of inertial structure and inertial frames. So it's quite nice from that point of view as an extra case study.
But dynamically emergent. Yeah.
I mean, in the strong sense, not in a fuzzy sense. You can define it sharply.
Yes.
Adam and then Simon.
Oh, thank you. I'm not sure how cogent this question is, but is there a concern that some of these equivalence principles, as you say, perhaps not in full agreement with Dennis, but we should construe them as bridge principles that connect distinct theories. Is there a worry that we can't therefore expect any kind of rigorous formulation of what they say in the framework of any theory? Is there something sort of irreducibly informal about them, or is there some hope that we can actually make sense of them saying something, as it were, in a particular theoretical framework?
I think you can make sense of some of them in a so for example, in the context of a geometrized theory, it seems to me okay to make sense of SCP-1 as I stated it, but you can't make sense of this guy in the context of a geometrized theory. And maybe you might think that the theorems which relate them are sufficient to map concepts over here to concepts over there, but that's like a thorny Phil-sci issue.
Yeah, so is it that some of those arrows denote translation and some of them denote entailment in the same language?
Yeah, which is, it comes back to Oliver's question, I think. It's a little misleading about this diagram. But I think that, don't you think that in the geometrized theory, you can state this guy, for example?
Well, for some reason I was thinking about EEP.
Right.
I think people who are learning general relativity for the first time find it incredibly helpful to hear something like the claim that gravity is inertia, or motion under gravity is inertial motion. But it just strikes me that if one were attempted to sort of express that within the framework of general relativity, it would be impossible. It would just be a tautology, I guess.
One just has to say something like, you're working with the Levi-Civita connection, which is not as illuminating for sure.
Yeah, thank you.
Simon?
Sorry to be slow. Yeah, well, there's two conversations going there that I quite like, but let me focus on the one with Ollie and the issue of miracles and so forth. I do think that there is a role for a certain kind of conceptual analysis or foundationalist approach or whatever that does make something that previously had been taken as somehow factual, not itself an object of concern or inquiry, and makes it one. So an example would be the weak equivalence principle, and so when you really start to probe and ask, well, how is it? Why is it that this ratio of gravitational and inertial mass, constant independent of materials and so on and so forth, that it can actually deliver something? And I think there are other examples of this sort. In the case of the various miracles that go with the dynamical approach, what I would have thought is needed to deliver, as it were, to make it appropriate to turn something that otherwise seems straightforward into something miraculous, is that there's some further thing that you do with it. So you understand, to make something that seems straightforwardly conceptually unproblematic into something deeply problematic, and then do nothing more with it, that seems methodologically wrong.
Right. So if we're thinking about what Harvey and Dennis and I called the first miracle of relativity, why do all laws manifest, at least locally, the same symmetries? So I guess I want to say two things. First of all, I'm not sure from my point of view, I'm not sure we generated that problem. It seems to us just a problem. We didn't deliberately manufacture it for no cause. But also we do try and solve it. And I guess not just us, but others as well have said some interesting things about this really recently. So I wrote something about how it might be solved in string theory, which I think is probably overkill now. There's a really nice paper which is coming out in Studies by Key and Salim Khani, showing that you can explain these miracles from the point of view of the spin 2 formulation of general relativity. And so it's not like people who feel the force of them are just leaving them there. They are also trying to do work to say something interesting about how to solve them.
No, but jolly good. Really, I wasn't saying you haven't done anything with them. I was just making a point about what is good methodology, as it were. And
yeah, agreed.
It can be very wonderful if it does lead to some further exploration. But yeah, good. So I'm glad to hear that some of those miracles are no longer quite so miraculous.
I just want to advertise to people Kian's paper. I thought it was really amazing.
There don't seem to be any more questions, so unless anyone's very keen to jump in now, seems like a good time to end, and to thank James for an excellent talk.
Thank you all. What happens now, Alex?
I think I end this and then I can start up the other one.
Yeah.